Hi everyone, I'm Jaime, a PhD student. My supervisors are Alberto Vela and Miguel Perez. Um, the topic of my thesis are the trend bands in turbulent mixing, but before to speak about the trend bands, I want to give a brief overview of what is the turbulent mixing problem. How is going this? Perfect, okay. The turbulent mixing problem basically consists in the mixing of a diluted species into a turbulent background flow. And the task of the turbulent is to intensify the gradient of the concentration and to stretch the laminar structure of the diluted species. Some practical cases of the problem is the mixing of the fuel in combustion, for example. And another one is how is the behavior of the concentration of the pollutants. A characteristic, a relevant characteristic of this problem is that for similar cases, doesn't matter the initial state, that the final state of the system will be always the same. What I want to say is that between the initial state and the final state, that way can be very different from similar cases, and that way is what we call the transient. If we look to the figure on the left side, we can see three cases with that blob is the initial condition for the diluted species, and the initial condition for the turbulent background flow is the initial condition for the concentration for the diluted species is the same for the three cases, and the initial condition for the turbulent flow that is in the background is different. And what we have there is that the evolution of the system for that three cases is very different, only changing the initial condition of the turbulent that there is in the background. And in the video on the right side, what we can see is a histogram of the concentrations in a temporal evolution. And what is relevant there is that histogram has a heavy tail, what is saying us that the probability of finding external scenarios, external banks, peak of the concentration, is not negligible. So what we are looking for is a base model for predicting that external bands in a chaotic and transient system. For instance, what I have here is the decay of the maximum value of the entire domain of the concentration for several simulations. The concentration goes from 0 to 1. And if, for example, we see to the value 0.4, what we can see is that time until to achieve the value of 0.4, starting all the simulation in 1, the time to achieve that point is very different from the different simulations. For example, there is a different of 2 units of time for a case with the same initial condition of the diluted species and different initial condition for the turbulent flow. And what has been done until now in the literature, what mainly have been analyzed is the length and time scales of the mixing. Also has been analyzed the steady state flows with ad hoc gradient of the diluted species. And the transient has been analyzed, but considering ad hoc assumption to close the problem. So in general terms, the current mixing models can capture some aspects of the turbulent in the problem of mixing, but they really fail predicting the probability of finding extreme events, the peak of the concentrations. With respect to the methodology, we have used a DNS solver to have all the information about the system. The turbulence is homogeneous and isotropic turbulence, with the point of evaluating the behavior in the initial range of the spectrum. And we have analyzed the problem for different Reynolds and scales of the diluted species. Respect to the model, the turbulent flow is modeled by the Navier-Stokes equation for incompressible flow with a forcing term to keep the turbulence going. And the diluted species is modeled by an advection diffusion equation that is called passive scalar. And the mean parameter of the simulation is the Smith number. That is the ratio between the momentum diffusion and the mass of diffusion. That it is 3:1. This is due to a trade-off decision between cases of interest and what is computationally possible. So in summary, what we have is a transient system. We are looking for a universal statistical model covering all the possible variation in the evolution due to the different initial conditions of the turbulent flow. And we want to reduce the complexity of the system to the range of parameters of the simulation and the scale of the diluted CPC. So another way to approach this problem is with a massive ensemble simulation. And for the results, we have run around 15,000 simulations. A way of understanding these external events, this peak of concentration, is considering the maximum value of the concentration in the entire domain. I mean, here is temporal evolution. So to track that value, what we have defined a variable called the sinus decay. That this is the waiting time required for the maximum concentration to drop below a threshold. As a first result, what we have is that sinus decay is modeled by a log normal distribution. And with this, we can reduce the complexity of the system to two parameters that they are the parameter that they are defining the distribution. And in the right figure, what we can see is that if we scale the log normal distribution with the parameter that they are defining the distribution per each threshold, all of them are collapsing one onto each other, showing that the model is working, the characterization is working. And as a second result, if we look to the maximum value of the concentration in the entire domain over the time, and we try to fit it with an exponential law, and we do an ensemble simulation, and we compute the median of the time of decay, we find a model for the median of the time of decay that is a linear model respect to the logarithm of alpha. Gamma, the decay rate, is computed computationally. So what we have with this second result is a half-life model for the maximum concentration knowing T0. What we found and what is next? We have found two models to characterize the time of decay or the maximum value of the concentration. But we don't know yet how the parameters of the log normal distribution and T0 are scaling with the Reynolds and the scale of the scalar. And we need to do this to close the model. And aside of that, as a work in progress, we are analyzing the geometry of the scalar to characterize how is the distribution of the concentration affecting to the decay of the maximum value of the concentration. And we are looking for an estimator of the maximum value based on low order moments due to the systems of mixing model that they are based on them. As conclusion, in summary, we have a model for the time of decay of the scalar below an arbitrary threshold. A chaotic system has been reduced to a log normal distribution defined by only two parameters. We have a model for the half-life of the maximum value of the concentration in function of a T0. And we are looking for closing the problem in a model based on the Reynolds and the diameter of the blob. And I want to say that we are building a framework for predicting critical representation for safety standards and other applications where the strain event, the strain concentrations are closer. Thank you.